this is the, I mean, I'm surprised that some of you did not visit Big Bear. I mean, in the field a long time, probably that's our fault. We did not hold many meetings there, so maybe we should. Phil was talking about the fishing, right? Is this a good place for that? It's a big lake. For the solar physicists, so we all know the big lake has an advantage that stabilizes the temperature. That's the reason a high mountain lake is a good site for solar observation. So that was a major contribution of my physics advisor, HAO after NJIT took over the operation of Big Bear Solar Observatory, we built the 1.6, used to be a new solar telescope. Last year, it's renamed as a Goode Solar Telescope, obviously because of his leadership in building this facility. Some of you probably already know there's different instruments. A lot of instruments are very similar. It's a miniature version for the decast. There are some instruments, including adaptive optics, the visible image spectrograph, and near-infrared imaging spectrograph system. And also there's a cyanogenic infrared system, which decast will have too. Of course, the broadband image. I just go through very quickly on those instruments. So I especially want to talk about the AO, the adaptive optics system, which is also a very, it's a key for the operation of ground-based solar observatory, because the atmospheric seeing, usually no matter how big your telescope is, if you don't have adaptive optics system, your telescope is acting like for diffraction limit wise, it's like only a few centimeters. So if you don't have adaptive optics, so this is why we're building adaptive optics, starting with AO76 and 308, and the third generation is more or less working. It's a multi-conjugate AO. And all those are as a part of a collaboration with the National Solar Observatory, and is in a big picture for the decast. This is like a test bed for this kind of development. So of course we use image speckle. Reconstruction, so-called speckle reconstruction. So you take multiple images and then combine together to eliminate a seeing. So now you can get for our 1.6 meter telescope, is for all the images. Pretty much after this exercise, we can get diffraction limited images. For the instrument, I probably just show this. This is a traditional AO. This has been working at Big Bear for the last 5 or 6 years. And what you note that is correction is best in the center. Now it's changing to the multi-conjugate AO. It will show the original one again. In a classical AO, the correction is around the center of the field of view. This is a classical adaptive optics. Here it's sharply corrected, and the edge is not. But when you take care of the multi-layer atmosphere, now it's corrected to the pretty much the entire field of view.
How big is that field of view?
Pardon me?
How big
it's around the 80 arc second. So I don't know what the decast target field of view.
120 minutes.
120. 120. It's bigger, right? Okay. Okay. So then I just quickly go through. This is a tunable visible. The visible image spectroscopy system. You're going through a HRV line. By tuning the Fabric Pro, then you can get a different layer of the atmosphere. When it goes to HRV line center, you see high up. In the wing, you see lower in the atmosphere. This system works very well. FIS is developed by our partner in Korea. it's a faster spectrograph system. It doesn't have a polarimetry capability, only just the spectrometer, but it can scan very fast. That's the advantage of it. You can get an entire scan of like 60 arcsecond scan in around a minute. So it's a very, so you can get two channels, usually put in H alpha and also calcium in near infrared. Okay, so those are some very nice face image. And this will be the Big Bear's key instrument for the research. It's NIRIS. It's a near infrared. It's a dual fabric pro near infrared magnetograph system. So the field of view is 85 arcsecond. I will show a lot of images associated with that. So you use a 1.56 micron, very famous line. We can get if we to use it without any interruption, we can get the cadence around the 40 seconds for entire set of the vector magnetogram. And in this field of view, and we also can run in the 10A30, which of course the challenge is the inversion to derive the magnetic field from the chromospheric line at 10A30. So this is we have all the hardware for the 10A30. For the 1.56 micron, it's working very well. So those are some examples of the high impact papers. We in the last maybe pretty much last 5 years, that's most of paper come. Well, we have over 100 publications. We have a number of papers in the Nature subjournals. So I will introduce a few few papers representing what did not see before. And this was a very earlier one, 2015. And it was the first time we really can use the H alpha to look at the process of the erupting flux loop. When the flare happens, you really can have map the flux loop, and then you compare with a nonlinear force-free extrapolation. So with such a high resolution, what we found is a convergence flow around the sunspot light, polarity inversion line that trigger the eruption. Then we have the twisted flux loop coming out. So this paper pretty much discussed the mapping from the H alpha and comparing with a nonlinear force-free extrapolation. They match very well. Then we have this paper in 2016. It's in the Nature Scientific Report. This is the very first time the flare is observed in such a high resolution. You probably can see the two episodes of the pre-flare called a precursor. So this is why we now think at least a lot of events. They started with a very lower atmosphere, the flare. They have the precursors. In the high atmosphere, the magnetic fields are in a configuration of the non-potential state, but you need some triggering. And our senses is they are triggered a lot of times by the lower atmosphere. I probably should show again.
So which wavelengths is that?
This is H alpha. This is the H alpha red wing, 0.6 angstrom towards the red side of the H alpha. Then you see the eruption. Then you see the typical two-ribbon flare and the post-flare loop. So what we can see in this paper, we actually can find the very fine structure of the post-flare loop. It's pretty much in it's like a 1 to 200 kilometers. It's very narrow, and then we can find a narrow moving ribbon. It's also around 1 to 200 kilometers, and with a strong redshift. So that means you have things coming to the surface. And what if you pay attention to is a post-flare loop called a secondary emission. If you, probably I should play it again. You can see this is the main ribbon. Then in the post-flare loops, this is the first time we can see the very tiny brightening during the that's a condensation and the material coming down. Since there are enough resolution, we can see this material cause a secondary brightening. So that was not, it's observed in a large scale for those called a coronal ring, but in H alpha was not observed before. But there are a lot of things we don't understand, and here you can see what is the whole sound. One part of that is this field of view, and then this tiny bit of that is our Big Bear's telescope. And we do a lot of analysis. We found that it's very narrow, so I don't go to detail, but those fibers are in 100 to 200 kilometers. So I know that I talked to Kevin, and I know that Dickus will look at the size of the 20 kilometers. So that probably we will ask the question, if we go there, do we see the flare, the post-flare loops, how they will look like. Okay. And then we found something else also very interesting. Use 10A30 is a very special line. Since the 10A30 is formed when the two electrons in helium are in the same spin orientation. So that's called a helium triplet. Okay. So usually they don't, we don't see it, but the reason we can see the 10A30 is because of some ionization process. You set the electrons free, the atoms free, and then they come down to the triplet state of the helium. What we found here is a very interesting thing. Here's a flare ribbon. It's a different flare. It's in 2013. Then can you see in the front there's a dark ridge, the propagating? You would think that might be you do a heavy image processing, so you have that. But if you don't do any processing, just use a raw data, you still see it. They are just not as contrasty as this. So this actually, the narrowness is agree with H alpha, although it's a different flare that we saw. It's around 100 to 200 kilometers. What causes this? Okay, so we give an explanation is due to a collisional ionization. So it only happens in the front of the flare ribbon. The collisional ionization will set the atoms to a free state, and then recombination will set into a triplet state. And that, if the flare is not strong enough, then you can have the absorption lines showing absorption. So we give a name of that. It's called a black light flare, so it's absorption instead of emission. Okay, so it must be related with the must be associated with something with the atmospheric structure, and also some special case of radiative transfer. Okay, so this kind of things we did observe in another line. It's also in the helium line. It's D3 line, helium D3, with older Big Bear data at that time. actually it was first pointed out by Hal Ziering, but we look at his original paper, did not show something like that. I mean, that striking. But later on, we analyzed some digitized film. We did see that. So that we're actually, with this one and a previous paper, we have one very very interesting science question. You know, Phil was a member in our already finished Living with Star project. We look at the flare emissions at the foot point. There is one key question is, when the electron come down, what's the area that come down? In most of the flare foot point, people observed before was like 1 arcsecond or larger. Like RESI observations is 2 arcseconds. So a lot of modeling use that as a source size. Now we can find the flare front is where the electron comes from. It's only in the order of 0.1 arcsecond. So if it's order of magnitude smaller in a one dimension, the second dimension probably it's okay. This along the ribbon in a one dimension. So that means the electron density you coming down will be an order of magnitude higher than previous models used. This has been a very interesting physical question. Some of our collaborators use a higher flux to calculate using the models, but the models won't work. So, but the observation require that very narrow source, and but model cannot do it. So now this is a challenging question. Okay. Okay. So this is one paper received a lot of attention. It was in 2016, and there's a title called "Tail Wagging the Dog." It's a Nature Physics called News and View reported our article. The basic idea is just we know the corona is density is very low, and the photosphere, the density is high. Okay, usually it's something happening in the photosphere can drive the corona, but the corona they treat it as the tail, and the photosphere people just treat it as the dog. Okay. So then basic question is the dog can wag the tail, but can the tail wag the dog? So that's the question in that Nature Physics article. They refer to this issue. But we kind of find some evidence that after the flare processing in the upper atmosphere, that can also wag the tail. Wag the tail can wag the dog. So that's I probably can just show some of our previous studies. We always found the after flare, the magnetic field structure will change in the photosphere. So that's evidence in many papers with HMI data and also older Big Bear data. So if you do any experiment, you do this test, it's before and after flare, you do a subtraction of the two images, you always found center brightening with a dark ring around it. So that means you give an impression, the center sunspot become darker, the surrounding it becomes lighter. So now this becomes a rule. It always been like that. And it's pretty much a step function if you use magnetogram to so that's post-flare the appearance. And this is what our earlier study from our GST observations. Before the flare, you don't have a connection between two sunspots. After flare, the connection appeared. And if you do a time-space diagram, you will see exactly at the flare, you have a connection. So this has been a question. So what happens to It's not only that we can see that in the 2-dimension, you see the 2-dimensional structure change. And this is the paper by Hugh Hudson and a group in HAO. They did using a very simple principle called the conservation of the momentum. They predicted actually is what we found near the flare in neutral line. The magnetic field will be enhanced after flare. So they call this a back reaction. Then we extended to so-called conservation of the angular momentum. If the eruption carries a lot of momentum in one direction upward, there must be a if the entire system is an isolated system, then it should be opposite direction angular momentum that can drive so-called rotation in the photosphere. There are a lot of studies on that, and also we did some calculation. The very early study is by many years ago. It's this paper used the MEES data. They kind of saw the sudden motion in the solar photosphere after the flare, but it was not that convincing. So this is the best convincing example. Here is a light curve of the solar flare. Just look at this window. Can you see the sun suddenly rotates? Okay, and this rotation only happened in a very short period after flare. It did not restore. Okay, so we use initially we just use some to treat it as a rigid body motion and feed it this feature and found this angle. Then you can see when flare happens. This is pretty much like, it's not exactly step function, but it's like arrow function. This before flare, suddenly there's a sunspot that rotates around more like 12 degrees, just suddenly rotated in a time scale of about 2 hours. And then it did not rotate back. It's a permanent rotation, okay? This is a more detailed, this is a TIO image. You probably see that in the TIO image, the flare is just like flash. It's if you see that around here, the flare, it's not easy to see. But in the H-alpha, you can see the flare much better. This is the H-alpha, the 1 angstrom, and then you can see the flare ribbon is moving differentially. You can see those are very concentrated, narrow flare ribbons. They are going through this surface. And then what we found is this rotation. And when flare ribbon propagates, we found that this rotation this particular area starts to rotate exactly as the ribbon gets to that point. So it's just like a ribbon is, so that's why we call this differential rotation. It's not a solar differential rotation. It's a rotation that gets, it's not the entire active region rotates at the same time, but whenever the flare ribbon hits that particular area joins the rotation. Okay, so it must be, it's called a back reaction to what's above us. Okay, and we did many exercise. We especially calculated its the parameter and the pointing flux. We found that this one pointing flux that do come from the it's from up to bottom. It's propagating from, so that the action comes from the upper atmosphere. The reaction comes in the bottom. So this matches with that scenario, so-called tail wags the dog. So this is the first solid evidence that solar flare can trigger some sudden motion in photosphere. And we did some calculation with Hugh Hudson's equation. Actually, they do match. It's we use the conservation of the both angular momentum conservation and momentum conservation, we think at least the order of magnitude matches their scenario. It's a back reaction to what's the above photosphere. And then in a very recent one, we do that even further to study the vector. At that paper, we didn't have vector magnetogram. Now Big Bear provides a vector magnetogram. We now do a very careful inversion, and data is fully released for our 1.65 micron observations. Then we also compare our data with the Big Bear data with SDO data, HMI data, and also we compare with the Hinode data, the SP data. We found they match reasonably well. So that's how we can release the data. This is from the HMI. If you run the movie for the same sunspot area, this is their transverse field. You can see right after flare, transverse field becomes enhanced. This is not new. It's from HMI. Basically, to make it very simple, it's just that you have something push the fields down and then stay there permanently after the flare. Okay. From HMI data, you can see the propagation. This is a difference image using the after flare, before flare. You can see this enhancement starts at the center and then propagates to, as the flare ribbon separates, that propagates following the flare ribbon. With the Big Bear data, so this is the same Big Bear data. Then what we can do so-called a time-space diagram. This is a time and this is a space. And here this is a dark contour here showing the flare ribbon. So what you can see is the field change again following the flare ribbon. So that gives us kind of a picture. Whenever the newly area got reconnected, the field topology also got changed. And then we did the plot of the many points along the ribbon. Then we found a lot of time is this kind of step function. It's not exactly a step function. It's a sudden jump, but that jump did not come back. And there are certain points, I will get that later. There is a so-called impulsive change. So that means a transient. It only happened during the flare. Also we use the HMI data. We also can do a 3-dimension. Okay. So this is have nothing to do with Big Bear data. In order to get the corona field, we have to use a larger field of view. So that's the HMI data. Then we can do a 3D map of the magnetic field. Then this is I think it's a S1 in this area. We do a cut. Then immediately you will see what happens is the field near the polarity inversion line, that becomes they turn around. This is a 3D image, but we cut in a like XZ plane now. So then in a 3D, we can demonstrate what kind of elaborate what we observed in the 2D. In the 2D, we only can see near the neutral line, we see the field got enhanced. So that means there's more connectivity. And far away from that, we see the fields got, this is a S4, it's far away. Then we can see the field got more straight. Okay, so essentially what happened is in the polarity inversion line, the fields are pushed in and far away from the active region. the field becomes more vertical. That's what we found. And that it can explain all the things what we found so far, but it cannot explain the rotation yet. So we also collaborated with people into the simulation, MHD simulation. This kind of change of the transverse field enhancement after flare is actually showing a simulation. The earliest comparison we did with Yuhong, that's a few years ago. And although her simulation at that time is only 2D, and we had a paper compared our observation with her simulation data cube. They match it very well. But now we need to compare this 3D to understand what's going on. Okay. And we also last year we published a paper in the new journal Nature Astronomy. This is the first time we collaborated with Kasuna in Japan, since he has some famous scenario talk about the triggering of the solar flare. Again, it's near the surface. This is his famous diagram to look at the probability when the flare will happen. The flare can happen, we all know, if we have so-called let's look at this axis, is shear. It's when suppose that you have a polarity inversion line like this, the field just connect from positive to negative. This you call a potential, right? You call a potential field. And then if you start to slide it one polarity relative to the other, then that's called a magnetic shear increases. When you get to almost exactly like that, the field got parallel to the polarity inversion line, you say the most sheared. Okay, as shear increase, you're going to have a higher chance to have flare. That's a well-known scenario. The shear is just builds the energy, so that's from potential to the shear topology. And there in this axis, that another way to show the complexity is if you have a simple neutral line like this, okay, it's less likely to have flare. But if you're going to have some polarity inversion in this neutral line, like this will become positive, negative, this kind of topology, then it's more likely to have a flare. So the most likely to have a flare is the complexity of your polarity inversion line plus high shear. So this is why the red concentrates right here. This is from his numerical simulation. He can use this different topology. I don't go to the detail of it. This again shows our comparison. This is the very first paper we use our vector magnetogram. This is from Big Bear. It's from Hinode SP, and here is from HMI. You can see they are very similar. This B line of sight, this transverse, this is the azimuthal angle, the angle in the XY direction. They highly agree to each other, all three. But you kind of can see Big Bear has the best resolution. And not only the resolution, since the SP, if they scan a reasonable size of the active region, it takes an hour or two, but Big Bear is 1 minute. So now this is, I think we, at this moment, we have a unique instrument which produce vector magnetograms in an 80 arcsecond field of view and with 1 minute cadence and around 0.2 arcsecond resolution and can last a few hours. So that's the unique product of this of Big Bear. So in our some study, like a very, very early paper I did with Hal Ziering in '93, also in the Nature, we found that there are indeed some active regions with a very complicated polarity inversion. So like a region like that, I don't think I can identify a polarity inversion line since there's positive, negative, positive, negative. So more like that, more likely you're going to have flare. So this is exactly like what the Kasona they pointed out. Not only the shear probably, I mean, it's 180 degrees, but complexity is another important thing. So in our paper, we this is actually it's the same flare we did. We see the flare has the precursors, and we just want to see what happened to the precursor. And in the precursor area, we really can see those are the patches, some H alpha initial brightening, and we did the. So this is a kind of movie, an iris movie now we have. The first of that is that we can see a lot of dynamics which we didn't see before. Like this is where the polarity inversion line and where the flare happens, this flare happens. Then we see a lot of mixed polarity come out of this active region, and especially the initial brightening of the flare. We can see we do a very careful analysis. This is like a Cosenna's model. We have a main neutral line, but we also have a very complex polarity inversion in this area. Then we did this analysis of in the flare trickling area. We did a flux analysis. We also did an electric field analysis. This is electric current. This is another way to indicate the complexity and non-potentiality of the active region. Then we did found that there is a temporary enhancement of the complexity in the flaring triggering place. So that's why this is still ongoing project. We still find a lot of flares do have the precursors. The precursors might come from the complex area which has a lot of dynamics like the flux emergence and cancellation. So this might be the trickling point. Doesn't mean the energy storage is that place. It just means you have a highly unstable system, but you need a certain trickling. So that's shown by Cosenna's MHD simulation and also our initial observation. And also for the same flare, we use a radio to prove the initial emission comes from very lower atmosphere. So what we can do is during the flare, we can do feeding, this gyrosynchrotron radiation feeding. This turnover frequency indicates where the magnetic field is. Okay, that when magnetic field increases and this peak frequency will move to right. And with this kind of feeding, this is another NJIT facility. It's in Owens Valley. Professor Deagari is operating that facility. So what we can see when the flare precursor happens comes from 1500 Gauss field area. So that means it indicates that indeed it comes from very low in the atmosphere. And then this flare emissions gets from 1500 to 500. So that emission gradually get into a higher atmosphere. So that just demonstrating the importance, okay? And this is one of the PhD students. Since to save time, I just oh, sorry, this one is another thing we don't understand. I just want to mention that. And we found in a flare, usually there's not much, not like HMI movie. If you look at HMI movies, you will see during the flare, you always see so-called Magneri Transient. Okay, it's where the line profile changes. Your flare induced some apparent magnetic field structure change. But this is one of the papers we also published this year in Nature Communication. And we found that when the flare happens, we normally don't see anything in either line of sight or transverse magnetic field. There are a couple of reasons for that. The probably most important one, we are using 1.56 micron line, which this line forms in so-called opacity minima. So that means you can see the deepest into the solar atmosphere. So that means when flare happens, you hardly can get any signature there. So that will protect the magnetic signal. But we found that although the line of sight field does not change, transverse field does not change, as mutual angle changes. You probably can see a ribbon propagate. Okay, so we did a very, very careful analysis. We still don't understand what's going on, but we already shown it's not due to the atmospheric structure. Line profile. We did a very careful, since line profile does not change. Okay, we raised. I just give those explanations. We make but we actually, in our discussion, we exclude most of them, except this is pretty much the only one. We think at least we don't have evidence to show that it's not this possibility is not excluded. Probably we see a signature of the Alphen wave that comes down, and that can make this kind of change, which does not change the field strength, but just change the field orientation temporarily. Originally, we thought it's induced the B field during electron beam. This is one science question we've been asking. Since if you have an electron, we all know the flare ribbon is due to the magnetic reconnection in the high atmosphere, then electron coming down, right? When the electron comes down, if they come down very quickly, and the protons cannot come down with them that quickly, since if protons are moving at that fast, that will produce so much energy. So it's only the electrons coming down. If an electron comes down, that will separate charges. So that creates the electric current sheet. You just imagine there's a wall, there are a lot of electrons like rain falling down to the surface. But of course, there are some issues that people say there's a return current that can balance with it. But this is some issue we're still debating. So this strong current sheet could induce some extra field. Okay, so initially we trying to use this one, and we found that you can expand part of that, but it cannot expand the other section of it due to the induced field will have certain orientation that will increase or decrease the field that can change the orientation of the B field. So, but anyway, this is still, as I said, a lot of things we don't understand. We just see it, and but we think that probably the Alphen wave might be still a possibility. Okay, and also as I said, the not only magnetic field is so dynamic when the resolution is high, you also can see the velocity field. Like this part of thing, we really don't understand it that much. We can see in some sunspots, the flows are really high, and here can get to like 3 or 4 kilometers per second. After the flare, especially in this section, the flow enhanced a lot. This is where the flare happened. You see this is before flare, and you kind of can see after flare, they really enhanced a lot. So that means the penumbra structure changes a lot after the flare. Again, we use this time slide diagram, the time and the space. We can see those enhancement of both the penumbra structure and the penumbra velocity. There's a sudden enhancement is associated with a flare. So what we can see now, So probably this part I really want to comparing with the modeling is the some section of the penumbra is very thin. We're seeing a very thin layer. When the flare happens, you push it a little bit, make it higher or make it lower. That changes the topology quite a bit. So so this again, it's in our observation. It seems like we are seeing a layer that can change quite a bit. If you have a disturbance, then the field lines can becomes when that becomes more vertical, you don't see it. When you don't see it as a penumbra, it becomes horizontal, then you would still view it as a penumbra. So this is some part, okay. And I just want to show another very interesting thing. It's we probably all know this active region, 12673. Especially actually this day, this is a typo. This day is X9 flare, right? On the 6th, and September 10 is X8. Okay. This active region was well observed and studied by many people. Started with a very simple active region, and then and then there's a bunch of flux emergings. This is like so one flux emerging. There's another one. Then that form very strong neutral line. That's where a lot of solar flares, and including this X9 flare. So it's very interesting to look at this active region. But Big Bear did not observe from the beginning, and only observed a part of that in the June, in the September 6th. We also found that for this active region, it created really a big white light signature. This is something else that's very interesting, and we use a so-called equivalent area to describe how strong the white light is. And before this flare happened, this is a log scale. The strongest white light flare is right here. It's just like our index is just a few, like 6 or 7. And now it's become 50. It's almost an order of magnitude showing the white light emission of this flare. But this one, unfortunately, very interesting, it did not have the SEP. So people thought it would have, but there are some explanations. I don't, but there's no formal. The SPD, SEP index, also log scale. The largest one was in March 07, 2012. And this is why we had a quick publication in the research notes in WS. So what we did is we found that Hinode has some very strange thing. This is Hinode data. In strong field area, they got saturated. So now we found that Hinode the inversion code set 5,000 Gauss as a limit. And what we did a very simple thing. Use the Big Bear data, directly plot the spectrum profile. Use Zeeman splitting. You can measure the field strength, and we found that it's close to 6,000 Gauss. And now so this is what happened. So now we are revisiting one scenario. I think Katie Laker had a paper, and she said it's very important. And after that, not many people look at it. That's like more than 15 years ago. She gave a talk in SPSS. Is for this kind of strong field, it's very hard to believe the surface flow can create that. It must be created deep. Okay, so that means we might be seeing this new flux emergings when they come out at a different time. We see different cross section of it. So those apparent flow might not be the real flow, but we just because we see a time evolution of the active region. So those kind of thing, it seems like it's a twisted flux near the surface, which is almost 6,000 Gauss. So we're trying to understand what happens. So we think they come out from from below the surface very rapidly. If you rising slow, it going to through the surface it expands, then fields become weaker. But if some emergence comes so quickly, like another paper by a Stanford group, I think this is the largest flux emergence rate. Maxwell per hour is way the biggest. So those strong fields probably kept at least for a certain period of time. So so this is something we and you kind of see it's a twisted flux system, but again we don't understand, especially in this section. That's where the flare happens. The most of flare triggered in this. And this is also the first time we see the delta sunspot. The neutral line is where observed and studied. Okay, and the microwave is also very interesting for the same active region. Usually the gyrosynchrotron radiation, the strongest is in the sunspot. But what we can see is that this neutral line, this is from Dale Gary's new imaging capability of Owens Valley, and also this is in the low corona. We can see 2,000 Gauss field. So that's from the microwave imaging. It's also unusually strong. I mean, that makes sense. 6,000 near the surface, then you got to the corona, you still see the 2,000. Okay, so I better wrap it up. I just shown that Big Bear not only look at the flares. This is our advantage. Since we can have a good seeing for 5 or 6 hours a day, many days in a row. That's why we catch many flares during our observations. But we also look at quite some. We just show 2 examples we recently found. One is the small-scale reconnection above the light bridge. That was published in APJ. Another one is a very recent one. We also start to use the NIRIS data to look at those structure. And this is a sunspot, the light bridge. And there's a ridges around it. That's well understood. Observed. Actually, Bruce Lights had a first paper on that from HAO. But what we found in those light bridge ridges, there are some patches we call knots. Then we analyze the velocity and the magnetic field with our vector magnetogram system. And this is a picture we're giving. There's a paper under revision. And we found basically the convection structure in the light bridge. The light bridge itself is very narrow, but has a convection structure. And there are some knots. They show the downflow. And most of the ridges here show the upflow. So that's the signature of the convective motion in light bridge, which we can compare with modeling. Here you have the expertise on those. Here is just my concluding remarks. Big Bear it's a unique tool to study the solar flares due to excellent seeing condition covering several hours a day. That's the uniqueness of the Big Bear site, and also it also provides observation of the fine structure of the sunspot. Some of the structure also need a long time following, like the dynamics of the filament. So far, our telescope has been productive, and we also think we will continue to play an important role in decades era. And so that's why I know that decades create many excellent user science cases. So in our announcement of our observing time, availability of observing time, we said many of those science cases can be tried with Big Bear, either existing data which accumulate a lot, or can we open a telescope at a time so we can make new observations. So then we look forward to a kind of collaboration. Since Big Bear and the DKIST team have been collaborating a lot, like focal plane instrument plus the adaptive optics system. So this is what we really want, the community from the decades, still 2 years. A lot of the very nice science ideas can be first tried using our data. There might be already some scientific results, and also that can help to plan the decades observations probably more effectively. So that's what we think. So yeah, if people are interested in using our data, either existing data or the new observations, they are very much encouraged to do so. Thank you so much. Questions?
So when you were talking about that case where there was not a change to the horizontal field or the vertical field, but there was a change to the
angle, yeah.
I was a little confused by that. Do you mean that the horizontal field effectively rotates?
Yeah, horizontal field effectively rotates, and magnitude did not change.
I see. Okay.
Line of sight field did not change either.
Okay.
I mean, of course, the first thing you would think is due to line profile, but we did a very, very careful analysis. It's not due to the line profile change. Yeah, the flare electron did not get to that layer. It's opacity minima. Anyways, John?
You know, the tail wagging the dog business is very tantalizing. There is one other example, and that is that the corona has put a torque on the sun and slowed it down. But this has taken several 100 million years, so we can't see it happening. But it's a big one.
Oh yeah, right. So that's yeah.
That's the only other instance that I know of.
Oh yeah, right. So it's kind of friction, right? Yeah. But this one is sudden. You know, you change it in an hour.
And there is likewise one that's likewise even more sudden, and that's the sunquake phenomenon.
Oh yeah, right. This is another thing that we look at into that. This sunquake, right? Can but we got some issues with that. Is the some sunquake they happen not necessarily at like hard X-ray kernels. So those are the places we very often see the like field change. So that's the.
But it would nevertheless be a coronal influence. You know, something that's probably the actual energy is very likely released from coronal magnetic fields.
Yes.
And then it has an influence that's, you know, in the solar interior actually.
Yeah. Right. Yeah. Right. Nina said she believe it's a combination of that then plus the topology. She thinks the key, she used that keyword is transverse field. The sunquake likely to happen where the transverse field is strong, the line of sight field is weak.
I'm almost speechless at being bedazzled by the remarkable observations, and I think you guys
Thank you.
have done a remarkable job. One of the things that strikes me is that the changes you're getting in the magnetism are really quite remarkable and unanticipated. I would not have expected to see the rotation of the sunspot.
Yeah.
And the cause and effect there is I think still up for debate.
Right.
So, but anyway, one of the things I wanted to get your opinion on. One of the things I think would be very good to have as a space asset would be a small telescope that can observe even just the longitudinal field from a different vantage point than the Earth, so that you can combine the Goode Solar Telescope and DKIST. I think it would be remiss of this community not to get an observation slicing through, getting a very strong longitudinal field component, maybe even a vector component, from a small instrument that is out in space, observing the exact same regions.
So you're using like a stereo type of the.
And it's very disappointing to me that we've been co-opted by the space weather community to observe things like CMEs, which are nothing other than the effect, not the cause. Whereas you're really trying to get at that, and I think instead of going for coronagraph observations away from the Earth-Sun line, we should definitely go to observe the solar disk and measure the most sensitive way we can with equivalent resolution. We can observe lines at 3,000 angstrom if we want, 2,000 angstrom with a small telescope and get the same angular resolution as you're getting with a big telescope. And we can pick those lines to form at various places through the sun's atmosphere. But this business of stereoscopically analyzing the vector magnetic field is very different from the one that stereo did, which is just looking at the scalar thermal properties of the corona. Again, an example of something where you're observing something that's already happened. The energy equation is the end result of it. It's the magnetism that's so important. So I just wondered if you feel that that's something you'd like to advocate for or not. Because my advice has been pretty much ignored by the community because they know how to do space weather, and that's where the money is.
Yeah, if we want to look at a different angle for a target, so no matter where you put on the Earth, your separation is too small, not sensitive enough. So there was actually in Chinese community, there was a proposal to put the magnetograms orbiting around the sun in a couple of places, just like a stereo, but not in the corona, but in the, so that probably, so the, since, the using the Earth as a baseline is too short, that's the, but of course, to join the large telescope or some telescope, form a network to monitor active region continuously, that's kind of collaboration that can be beneficial to the community. And also, like the idea, since each observatory may not be able to cover that many wavelengths, then you take advantage of different wavelengths to look at in a campaign mode. So that certainly will be beneficial to the community and to understand, as you said, very fundamental the triggering mechanism of the space weather. Yeah, I agree.
Here's another question. You pointed out very cogently this warpage in rotation, for example, that happens to the photosphere following the flare. And one suspects that this is a result of magnetic forces. That is, that the flare disturbs the equilibrium, and then there are now between the impulsive phase of the flare being
and the consequence
of that.
This is exactly what we are now to look at with our high cadence and spatial resolution together. So actually, to answer your question, we found that in the locally it's instantaneous. So that means suppose your sunspot is rotate, it's for the flare, it's a magnetic. Simplifies the picture of the flare is you have a flux loop cutting through arcade field, and then they got reconnected one by one, and they reconnected from the lower to the higher, right? So then we have the indication those rotation happens is differentially as soon as that locally got reconnected, they rotated. And then that it just overall seems like there is a 1 hour delay. If we use HMI data, it's always 1 hour delay as you observed. And but with the Big Bear data, now we can see it happens if we do that analyze point by point, we can see it's pretty much it's a step function.
Can you say that it's less than a minute, for example?
It's our cadence, which is about a minute.
Yeah.
So that probably decades that can look at even higher cadence, I guess.
And HMI can also, it has a cadence of about a minute.
Yeah, right. If you use the but HMI, if we
That's the spatial resolution.
yeah, right. We started to have a spatial resolution, but we actually trying to use our same technique. We know exactly what to look for. We now look back into some HMI data. We might be able to see that. We actually, in several cases, we already saw the HMI data see this kind of rotation as well. So it's just like with the initial analysis, if you're not looking at that, you just don't, you didn't see it or didn't pay attention to it. But because of the big bear data, now we can look back into HMI data. So we see the cases.
You do see it in HMI because
Yeah.
over the hour it's quite a lot.
It's quite a long, yeah, right,
And you
yeah.
also have a lot of pixels to do the statistics with.
Yeah, right, that's true.
In
So,
principle, you can
yeah, right.
measure much less than a pixel.
Yeah, right.
But
Since I now can see more papers using HMI data to look at this. It's just like initially we just people did not think about it if not that obvious.
Actually,
Yeah.
it is more.
Yeah.
It is more like you doing in your mind an inversion. And at low spatial resolution, what could add up to these changes that you are seeing could be other scenarios. With the higher spatial resolution, you find sort of a unique way to come to the changes that you see at lower resolution.
Yeah, I agree. So so now you can link both temporally and spatially to the phenomena. Yeah. Yeah, I mean HMI data been there for a long time. We didn't see those I mean, people did not publish, but now we look back, they are there. But you know, this is an advantage we get from the high resolution, and we can see the low resolution signature of that, but high resolution gets you more than what the.
Okay, let's thank the speaker again.